Hello, Øredev. How are you doing today? You good? Cool, because I'm good. I'm Max Arshinov, a solution architect from EPAM Spain. I work with different enterprise and cloud applications, and today I will talk about databases. So, why databases? That's actually a very good question because originally I didn't intend to create a talk. I was working on a set of internal tools, primarily for myself, because as an architect from time to time, I need to do architecture reviews. And I noticed that pretty much all of the reviews that I did during the last year included some observation on suboptimal database choices. So I was like, okay, maybe I need a more robust framework because I spent too much time describing these issues and trying to find the best recommendations. But I ended up having so much content that it turned into this session. So you might wonder what this QR code is. If you like to have the final framework, you can scan it right now or wait until the end of the presentation. That's a link to this presentation. So feel free to do it now or maybe later. And I will have less than 40 minutes to talk you through 50 years of database history, which is kind of challenging. If you feel like I'm trying to wrap through this presentation, maybe I am. So let's wait no more. Here's the agenda for today. Let's start with this specific question. Why is it so difficult for even seasoned engineer to select a correct database solution for their project? Then we are going to do a quick checkup with audience, check the existing database engines, check which ones of them are familiar to you. Then we'll discuss some important qualities that we need to consider during the database selection process. And we're going to spend the most amount of time on a slide with the timeline where we'll go through the history of databases. Hopefully, I'm going to make it on time, and I will wrap up this presentation with my key takeaway and the framework. So let's start, shall we? Why do people select wrong databases? Why is it so complicated? So first of all, we have too many options. If you go to dbengines.com, you will find approximately 400 options. That's just bizarre. That's too much. So maybe you tell me that you don't have to know all of them. You just need to be familiar with different kinds of database engines. But it's also confusing because sometimes people struggle to understand, okay, DynamoDB, is it a document database? Is it a key value database? What is the difference between key value database and document database? What are the columnar engines? Is it the same thing as white column databases? Or maybe these are the different things. So a lot of confusion here, and we are going to talk about it. And because of number one and number two, often people just give up and try to use marketing materials to make this decision. That's a terrible choice. Try to avoid this. But if you don't have any other options, maybe that's all you got. And last but not least, sometimes you just don't have the options because of the organizational constraints. We have little control over organizational constraints, so let's focus on first three. And let's check the DB engine types. Please raise your hands who are familiar with traditional SQL databases. Good, good. That's exactly what I expected. Let's talk about NoSQL databases. Please raise your hands if you know all of them. Okay, please raise your hands if you know at least half of them. Okay, that's pretty good. So more than 50% of the audience. So the thing is that NoSQL is an umbrella term that combines a lot of different database engines. And they are not only different from class to class, but even the same databases within the same class might be dramatically different from to each other. And lastly, there's also NewSQL database, which promises a combination of goodies from the SQL world in terms of strong consistency and high availability from the NoSQL world. And we'll see if it's the case and if it's that good as they promise. And also, that's just a single viewpoint. Another viewpoint is if we look at other important qualities, not only on different database types, but rather what are the trade-offs that these databases implement, or what are the features that they implement? Are we talking about in-memory databases? Are we talking about standalone servers? What about partitioning mechanism and sharding and replication and supported API and many more? And this list, it's even not complete because you can easily add more points to it. So, what I personally found helpful is to create this timeline. And I'm going to put different databases starting from the very beginning and briefly mention what it was important about this database and how it influenced the overall landscape. A quick disclaimer, I won't be able to explain any details, and there's going to be a lot of them. If you really want to understand the details, I highly recommend reading this book, Designing Data-Intensive Applications by Martin Kleppmann. And yeah, it's really worth it. Please raise your hand if you've already read it. Okay, quite a few people. So other people, if you need to just have a single takeaway, that's the best book on distributed systems. Okay, so let's go ahead. In 1970, Edgar Code introduced the relational model, and a decade later, Jim Gray defined the ACID, atomicity, consistency, isolation, and durability. These ideas formed the database landscape for the next 30 years, and SQL became a uniform language for data, simple, portable, and declarative. Vendors such as Oracle, IBM, and Microsoft implemented commercial solutions, and databases like MySQL and Postgres brought SQL to the open source world. MySQL had a simpler design, so it became a heart of the LAMP stack, and Postgres focused on extensibility. During the 1980s, databases focused mostly on operations, and by the end of 90s, those companies had a lot of data sitting in their databases, and they decided that they wanted to run analytical queries. And that's the point where OLAP was born, or analytical online processing. There were three versions of OLAP: relational, like Redbricks data warehouse; multi-dimensional cubes, like Oracle SBase; and hybrid OLAP tools, like Microsoft Analysis Services. While enterprises scaled up, some people wanted completely the opposite thing. And by the year 2000, SQLite puts a complete full SQL engine into a library. Soon, this database will become the most deployed database in the world, running on every mobile device, operating system, and web browser. But approximately at the same time, all database fits all the needs model kind of started to break apart. Øredev and KDB are very different first examples of time series databases. Øredev is arguably one of the first observability tools, and KDB is a database that is used for analysis of financial data. Lotus Notes use documents long before DocumentDB. And finally, the Lucene library implemented the inverted index data structure, and Splunk applied it to the logs. So search also became a form of a database. These are first examples of the thing that we later call NoSQL. There were three main business drivers for NoSQL to exist. First of all, by the year 2000, global big tech companies became truly global. And they requested the level of scalability and availability that has never been needed before. And the relational databases couldn't achieve this level of scalability. Also, despite that SQL was a very good language, sometimes some more sophisticated use cases needed a different approach because it was too cumbersome to implement these queries in SQL. And last but not least, there was some accumulated frustration with overall restrictiveness of the relational model because people started to work with semi-structured data. All these three kind of were the main factors that contributed to NoSQL. Let's talk about availability and scalability first. In 2003, LiveJournal implemented memcached because they had bottlenecks in their database. What do you do if you have a bottleneck in your database? You just cache the values. What do you do if you don't have a cache? You create cache. In year 2006, Google introduced their paper about a new type of a globally distributed database that was used internally in Google. It's called Bigtable. Bigtable was the first wide column database, and its design is dramatically different from the traditional relational databases. There are a few things. So first of all, Bigtable stores the data differently in group of columns that are called column families. So each row can has different combination of columns associated with it. So Bigtable was optimized to work with massive amounts of sparse data. 1 year later, Amazon also published a paper about their internal database, Dynamo. Later, it will be available as DynamoDB in the AWS cloud. So Amazon had a different issue. They needed to ensure availability of the shopping carts across instances in different data centers, especially during events like Black Fridays. So what they needed is to ensure availability no matter cost. And they achieved it by applying consistent hashing and a new type of replication that is called leaderless replication. Effectively, they eliminated a single point of failure, but they had to sacrifice consistency as a result. And open source alternatives followed up quickly. HBase is an open source implementation of Bigtable's ideas, but on top of Hadoop's ecosystem. And Cassandra is a wild beast. It was originally developed by Facebook, and it combined ideas from Dynamo and Bigtable. It took the data structure and scalability model from Bigtable, and it took the tunable consistency, consistent hashing, and leaderless replication from Dynamo. So it became a distributed, linearly scalable database optimized for write-heavy workloads, and arguably the most popular white column database in the world. As operational data grew, operational metrics did the same thing. So Graphite was one of the first scalable monitoring tools, and OpenTSDB did the next step forward because it was built on top of HBase, which inherited all the scalability goodies from the Bigtable's design. It's no surprise that the same scalability issue related to the volume of data affected analytical workloads as well. And the existing OLAP tools just couldn't process this amount of information. Columnar engines solved this issue. So in traditional relational databases, we store data in rows, which is good for transactions, right? But not that optimal for analytical workload. So what columnar storages do, they actually store different columns together. And this has three main implications. It supports better compression. Then we need only to query specific columns that exist on the query that we execute. And last but not least, we can run those requests in parallel, making them substantially faster. So MongoDB proved this concept in academia. Vertica and Greenplum implemented commercial data warehousing systems using the same concept. And sometime later, BigQuery added yet another concept to the mix. BigQuery was the first analytical database that introduced the concept of compute and storage separation, which means that we can execute database queries against distributed file system, and we can scale compute resources separately from the storage, which was a big deal for analytical workflows. Lastly, Apache Druid added some real-time ingestion mechanisms and stream processing to the mix, introducing a new subtype of analytical databases, real-time analytics. And yeah, we have Elasticsearch that took Lucene and implemented a scalable, developer-friendly search engine that dominated the world of search engines for almost entire time. Probably partially because of the popularity of the ELK stack. But not all the problems were related to the scale. Some of them were related to data structures. So Memcached was pretty fast and good, but it didn't support any data structures. Redis added data structures to the mix. And until this moment, this term, it didn't exist. People think about in-memory databases as caches. Starting from Redis, people started talking about in-memory databases. Also, Neo4j became the first commercial graph database, and it fulfilled a narrow but an important niche. Use cases like fraud detection or social graphs or recommendation systems, they all benefit from graph data structures. And Neo4j is a database that uses graphs as its data structure. And finally, in 2009, the NoSQL database was introduced, MongoDB, the most popular one. Not because it's the best one, but because it landed at the perfect time. It matched the popularity of JavaScript frameworks, and they promised greater flexibility and better developer experience. So MongoDB had the best marketing across all the NoSQL databases. And as a side effect, it popularized all other NoSQL databases as well. So by the end of 2010, we can see that the pantheon of NoSQL databases is complete. Redis is a go-to solution for in-memory databases, Cassandra for write-heavy workloads and availability with limited consistency, MongoDB for popularity and flexibility and web scale and other things. Neo4j is the default choice for graphs, and Elasticsearch for all kinds of advanced search capabilities. But this plethora of options also had some negative impact on the landscape. By this time, there was a specific name for this phenomena. It's called polyglot persistence. Martin Fowler defined it as a situation when any decent-sized company will end up with a bunch of different databases that are used for specific workloads and data structures. So some people were okay with that, but this kind of design comes with a cost, both operational cost and architectural cost. And some people, they just miss the good old times when we had a single database and probably a replication to an OLAP cube, and that's it. You don't have to think about like 5 databases and that are eventually consistent and how to synchronize them all. And databases like ArangoDB and OrientDB tried to resolve this issue. They were the first databases that were advertised as multimodal databases. What they did, they combined 2 data structures together under the same hood, documents and graphs. And then Couchbase did a similar thing, but it was a document database first, but it also added some in-memory capabilities. And what about traditional relational databases? Did they die? No, not at all. They did the same thing. Postgres added JSON and full-text search, and even some scalability extensions such as Citus. It's an extension that changes PostgreSQL and makes it a horizontally scalable database. And Vitess, developed in YouTube, does the same thing for MySQL. However, things were not that good for MySQL because after the acquisition by Oracle, a part of the team decided to create a fork, and this fork has a name of MariaDB. So one issue was resolved, or at least people were trying to resolve this issue by combining different models together under the same hood. But also, there was additional complexity involved. So during the last 10 years, we learned how to cope with massive amounts of data and how to make databases scalable, but at cost of consistency. And by doing so, we effectively just took the complexity from the database layer and put it on the application layer, because now you need to think about all the consistency issues in your backend code. And not everybody was happy about it, and many people wanted to bring ACID back. 2 peculiar databases tried to do it. VaultDB, probably you've never heard about it. It's a weird experiment that proved that we can actually combine strong consistency and high availability. But if we only run precompiled storage procedures, and if we have enough RAM, because all the consistency was achieved by getting all the information in RAM and also writing to write-ahead log. So it was helpful because it proved that actually we can combine those things together. Previously, it was one or another. But at the same time, it wasn't really scalable. We needed to make it possible to also create shards and replicate stuff. It's not really possible with VaultDB. So FoundationDB, which is mostly used by Apple, did a different thing. So that's a NoSQL database, and it only implemented a tiny core that implements a distributed key value storage with ACID guarantees, and all other layers can be built on top of it. So you don't build a multi-model database, you build a key value core, and then you kind of provide extensions. So you can build SQL on top of it, you can build documents and other things. And these two databases were the heralds of the new upcoming era of NewSQL. But frankly, the key database here is Google Spanner, only available in Google Cloud. And again, previously, it was only available in Google internally. So Google Spanner claimed that it effectively broke the CAP theorem and achieved a CA system. How did they do this? So Google Spanner utilizes two things: the Paxos consensus algorithm and the TrueTime API that leverages GPS and atomic clock. So it's effectively a hardware-software system that you can't really run on your commodity hardware unless you have atomic clock installed on your commodity hardware, which is unlikely. And at this point, we can notice a pattern. If there is a top-notch database implemented by a big tech company, there's going to be a really smart guy in the open source community who is going to implement the same concept, but in open source. This time it was significantly more complicated because of the atomic clock, and people needed to think about some more advanced workarounds. And I think also what happened here is the industrial revolution of databases, because we started using databases to build databases. Three of them are the most important one. LevelDB, originally developed by Google, that also leverages the LSM tree under the hood. RocksDB, it's a fork of LevelDB implemented by Facebook. And BoltDB is a similar tool, but it uses B trees and it's for Go. The first two are embeddable C++ databases. So what they did is they took those embeddable key value databases and used them as building blocks to build their distributed systems. These databases are used internally by etcd, an internal database for Kubernetes, or TIKV, a key value storage for TIDB, which both are part of the Cloud Native Foundation. And also inside of Cockroach, which is the closest implementation of Google Spanner that doesn't rely on Google infrastructure. Another noticeable pattern here is that cloud really matured by this time, and major cloud providers started advertising their database as a services. One of the first databases was Amazon Aurora, and these cloud providers, they quickly understood that compatibility was a thing, because they needed to migrate data from the on-premises data centers to the cloud. So what they decided is that, hey, we can implement our relational database, but let's make it compatible with both MySQL and PostgreSQL, so it's easier for people to migrate to the cloud. Cosmos DB did a similar thing, but they implemented two APIs, Cassandra Query Language and MongoDB. And Redshift and Snowflake implemented similar concepts for analytics. They're kind of SQL compatible. Redshift is close to Postgres. And Snowflake was a different beast. That's a cloud-only database, but this time it's not specific to any vendor. That's a separate company that runs multi-cloud setup. By now, there were enough ideas, and people started to think that maybe they don't need to invent anything else. We had plenty. But they thought that, okay, maybe we can optimize some of the existing stuff. What do we do to optimize them? ClickHouse took the ideas from Apache Druid and Vertica and implemented them in C++ using all the possible optimizations. Druid is implemented in Java, so some people may say that it's problematic for a database. And ScyllaDB did a similar thing for Cassandra. Again, Cassandra is implemented in Java. ScyllaDB is compatible, almost compatible with Cassandra because it uses the same query language, but it's a C++ database. Victoria Metrics is an optimized version that is compatible with both InfluxDB and PrometheusDB, because by this time people could have either of these options. And KDB and Dragonfly, they just shamelessly advertise themselves as drop-in replacements for Redis. And this shows how dominant Redis is in his niche. So, right now we are entering a new phase. AI is everywhere. It all started with Phase, a library introduced by Facebook, and then shortly some standalone servers appeared. Databases like Milvus or Quadrant. Most likely you will use vector databases if you work with GenAI solutions. If you ever heard about RAG, then you probably need a vector database. Even the term vector database is not completely correct because it has more in common with search engines. But we agreed to think about the search engines as a form of a database, so I think we can keep them right here. And here you can find even more examples of interesting databases, but they are all different, and I just don't want to go through them and discuss how different they are and why they're important. Just let them be. Wow, and I even have some time. That's really good. So, yeah, the most challenging part is actually behind me, so I can take a short break. I took the liberty to remove some outdated stuff or stuff that I think might not be really important for this presentation. Let's take a look at color coding right now. Everything that is orange is compatible with MySQL. Everything that is green is compatible with PostgreSQL. All the red database engines, they don't have open licenses, or they only available in cloud environments. And those green things, they implement various APIs. So like Victoriametrics implements InfluxDB and Prometheus, ScyllaDB implements Cassandra, Cosmos implements Mongo and Cassandra, and stuff like this. And I think it's really important because my first key observation here is that open standards, they win in long term. That's a thing, because we don't see many Oracle compatible database or SQL Server compatible databases except the one implemented by Microsoft itself. Secondly, relational databases didn't die. We still use them, but they adopted. They are actually now multimodal databases, and they are quite different from their original versions, because right now they have JSON support, they have sharding support, and other stuff. And no, we should not all migrate to NewSQL, because NewSQL comes with additional overhead. If you want to run such a sophisticated software, you really need to hire an expert who can help with all these difficult tools like consensus algorithms and being able to run it on multiple data centers, and they're complex. OLAP and warehousing. It looks like that's one of the rare cases where open standards don't work that good, because most of them are commercial or only available in the cloud. Except for maybe you want to implement your own data warehouse using Lakehouse, for example, but in this case, you will only have storage, and you will have to implement all the other components of the pattern yourself. If we try to summarize everything about NoSQL, then I believe that there is no right or wrong conclusion here, and we have some diversified outcomes. There are databases like MongoDB, which are quite popular, and there are databases that are still niche, like graph databases. We don't see that people use them frequently. And regarding vector databases and AI-driven systems, we are on a hype train right now, so it's too early to reason about them. Let's wait a little bit and see. Right now, pretty much everyone implements some kind of vector capabilities. Even Redis has some vector support, which is a bit strange. If we were to summarize all this plethora of options and try to extract the big ideas, and yeah, there will be a QR code that includes the entire presentation, just in case. If we try to summarize all these things, we only have 7 big ideas. The first one is SQL itself, so we are familiar with this concept. The second is that columnar engines are good for analytical workload, which is kind of straightforward, but still important to know. If we need a right-optimized storage, probably the best way to go is to use something that utilizes SS tables and LSM under the hood. So if you need to make this decision, just ask yourself if we are working with write-heavy workload, in which case LSM will work better. With a special case for time series databases. Leaderless replication effectively eliminates a single point of failure with a cost of consistency, but if you need availability no matter what, then probably that's your go-to solution. And storage and compute separation is a very cool thing, especially in the cloud, because we can store the data on S3 and request some resources on demand, maybe even serverless resources to run our queries. And yeah, we can achieve high availability and consistency at cost of latency and additional overhead, operational overhead, and overall complexity of the system. And probably this kind of system will be more expensive because of the complexity of this technology by itself. And multimodal database is a great idea. Most of the databases that exist today, they are multimodal databases. So how do I choose a database, or how do I validate if the database that is used in my project is the right one? The ultimate question of live database selection and everything is, are we looking for a versatile or optimized solution? If we are looking for a versatile solution, then the second question is, do we need both strong consistency and high availability? And it's really important, if we can tolerate all the complex operations and the overall costs. If the answer is yes, I do want to run my globally distributed and strongly consistent database across multiple data centers or even in a multi-cloud setup, yes, we have to use a NewSQL database, but you will need some experts to run this database. Otherwise, probably it's too expensive for you, and a traditional database, maybe with sharding support, is a better choice. Then you just need to ask yourself if you are working with OLTP or OLAP workload. And for OLTP, we have a choice between relational databases or document databases, because MongoDB is the closest NoSQL equivalent for the relational databases. It implemented ACID transactions. They're not that ACID as relational ACID. If you would like to learn more about it, there's a great website about it. It's Jepson.io. But still, arguably, there are a lot of use cases when these two databases like MySQL and PostgreSQL versus MongoDB, they might be just interchangeable. And if we need OLAP on an analytical workload, then we have a choice between real-time analytics, Apache Druid or ClickHouse mostly, and the traditional data warehouses like Snowflake, for example. And in case of specialized engines, we are getting to the NoSQL territory, and we need to ask one more question. Are we looking for a building block for a distributed system? Maybe you want to implement something like Kafka streams, for example. Good, just take RocksDB and implement your version of Kafka streams. Do we need some extra low latency or a cache? In which case, yeah, we need an in-memory database. At least that it might be Redis, or it might be another database that has this capability. If we care about latency and availability and pretty much nothing else, then key-value databases such as Dynamo or their equivalents, such as TIKV, for example, is the way to go. For write-heavy scenarios, the best solution will be a white column database, and we only have a few of them, and only single one that is easily available, which is Cassandra. For graphs, fraud detection, knowledge graphs, social graphs, and other kind of things, we should consider a graph database, but that's a really specific and niche use case. Most likely, you will not work with it unless you work with a very specific business domain. And for full text search, we should be using search engines, which happen to implement vector search as well. So there's a lot of overlap here, and the decision about having a dedicated vector database against a module in your search engine, or probably even a relational database, might be not that straightforward. And if we convert this framework into a graph, then it's going to be the following decision tree, which is quite small, and I'm pretty happy with it. Yeah, the only downside of it is that I had to read all the information about 50 databases to come up with this variant of the decision tree. And that's the checklist that I now use. Also very small, and I'm very happy about it. So let's how to choose or how to verify the choice. Let's define our service level objectives. Then let's classify the workflow. Are we talking about OLTP, OLAP, maybe both, and what kind of data structures do we need? Then we need to map the constraints. Maybe we only have one cloud available. Maybe we only have options in on-premises environments. Maybe we have a whitelist of databases, and our options are pretty limited. And then we need to also include additional capabilities that we need, such as change data capture, backup policies, observability, and all other stuff that are important to you. This is an open list that you can extend with anything that you need. Once it's done, don't jump into conclusions. Don't select MongoDB. Stay with the database class first. I know that it's complicated because we are selecting from multi-model databases, but well, at this point, we understand that multi-model can mean different things. It can be a relational database that added some document support, or it might be something like Foundation DB that was originally designed as a small key-value core where all the other dimensions and models are built as layers. So not all the multi-model databases are equal. And there's always the core model underneath, and we just need to know these implementation detail to understand what multi-model means for a specific database class or database engine. Then we need to decide whether we want to go with polyglot persistence or if we want to limit the amount of databases that we maintain. And then we need to create a short list of candidates. Once we have this short list of candidates, we need to document our decision in a form of an architecture decision record. And that's it. If you follow this workflow, probably you're going to end up with a pretty robust design document, and your colleagues will be very happy about it, and they will think that you're an expert in databases. That's how the design process might look like. So that's a made-up example because obviously I can't disclose any client data, but that's exactly how it would look like in real-world scenarios. So first of all, let's just define DB models at this point, DB model types. And I don't jump to the conclusions. I just think about relational databases, or maybe I need a columnar store, or maybe I want to use document store. And I just highlight with green, yellow, and red what is good and what is bad about every DB engine type. And here I have two candidates for this specific example, and I'm building a globally distributed SaaS service. I'm thinking about relational databases because I can achieve availability and scalability by utilizing shards, or maybe I need to choose a NewSQL solution, CockroachDB, for example. In this case, I decided to use CockroachDB because there was another important quality attribute requirement, which is I needed to implement multi-tenancy, and Cockroach implements this feature out of the box. So I was thinking, okay, in case of Postgres, it's going to be complicated to implement multi-tenancy, and there's additional cost, so maybe it's worth it. And yeah, so here we have Cockroach as our first candidate with strong competitors in the form of PostgreSQL and Amazon Aurora. And here, yet another example why I included the QR code. All these links are clickable. I collected a list of important papers where you also can read all the details about Dynamo, Bigtable, BigLake, Spanner, and other things. Jepson.io is the website that benchmarks databases and checks if their marketing promises are adequate. Mostly not. Mostly they're lying a little bit. dbengines.com is the website where you can start your journey. It's very helpful, especially if you don't know about a specific database. You can go there, click on the button, see what it is compared to other databases. So highly recommended. And again, this book is so important that that I recommend reading it right for the second time. Designing Data-Intensive Applications by Martin Kleppmann, the best book about distributed applications. And we have some time for questions.
Okay. Maybe stupid then, but why is a graph database great for fraud detection?
Why did I include graph databases for fraud detection? Because
What makes them so great for that?
okay, yeah, because some algorithms that I use for fraud detection they utilize graphs. I mean, not some, but like most of them. Yeah. Yeah, I know that's like a loaded presentation, but maybe you have like specific questions in your mind. Okay, we have a gentleman.
Nowadays, a lot is in Kafka. A lot of people talk about Kafka being some sort of database of the world. So, but it can store, it can collaborate. What is that? Is there any relation?
Okay, so to summarize, is Kafka a form of a database, right? Just in a single sentence. There's a talk about it. Martin Kleppmann, the guy who wrote the book, also delivered a talk on this topic where he showcased that, like, technically, yes. Practically, no, that's a message broker, actually. And the reason for this is that despite that we have some durability options in Kafka, it's another tool that was designed for other things. Yeah, technically you can store data in Kafka. And before Kafka was implemented, you know what was used for durable message queues? MySQL. Because people just didn't have any other tools, so they used databases to do something like Kafka. Okay, please. So I think I didn't understand all the important details about your question because it's really specific. But we can discuss this later, right after this presentation. Okay, anything else?